Hi guys, coming at you with a video about arc length and sector area. I'm going to start off by talking about what arc length and sector area are, and then I'm going to do 4 common examples. So let's get started. Essentially what's happening is this. We need to convert from degrees to lengths. We kind of do that when we talk about things like circumference and area. We're taking the 360 degrees of a circle and we are converting that into a length or a space. Now, there's a couple of things to understand here. For starters, a degree. What are 360 degrees? All 360 degrees is just a circle broken up into 360 pieces. There's a lot of history to why this has happened, and it's not necessarily coincidental, but that's how the ancients broke up a circle, and we just stuck with it. Now what we need to do is we need to take those degrees and convert them into lengths or spaces like square feet or square inches. So we could figure out a specific part of a circle. Why do we want to do this? Well, I was telling my students that I was amazingly shocked about how often this math is used. It is used in a lot of applications. In the design of wheels, the design of rims, the design of gears, the design of cams, camshafts, if you know what those are, which are all kind of mechanical parts. So rotating assemblies, all of that use some form of this type of math. So as abstract as it may look, it's actually a commonly used math in the mechanical world. Now, one other thing. The state that I'm in, which is the state of Georgia, historically has presented arc length in this format here, and sector area in that format here. What those are proportions solved. So this is kind of like me here trying to translate this idea, and I'm doing that for other problems. And what is essentially happening here is we can create a proportion, which I've covered proportions extensively, and so I'm sure has the YouTube. But we could create a proportion saying something like the part of a circle over a whole circle is equal to part of a circle over a whole circle. So we could do that. Now my circles look a little bit like crazy eyeballs, but that proportion will work. And all arc length and sector area are the proportion as I mentioned solved. That proportion is arc length over 2 pi r. So let's talk about this for a second. Arc length is this thing here, this part of the circumference. So this is the part, and then all the way around is the circumference. So that's the part over the whole, equal to theta, which I've come to call squiggly circle, over 360. So an angle over the entire circle. And the same thing applies for sector area. So we can write this sector area over pi r squared, which is the entire area of a circle, over theta or equal to theta over 360, which is part of a circle over a whole circle, part of a circle over a whole circle. Okay, now that I got that off my chest, let's get started on some examples. So what I'm highlighting here, before I forget, that is a sector area where the entire space inside the circle, or the footprint of the circle, is the area of the circle. Let's take a look at some examples. This equation here is asking us to find the length. This is the indicated length, so in this case we want like this bold space all the way around. Okay, so I'm going to use arc length formula. I'm going to just abbreviate that to AL. So AL over 2 pi r is equal to squiggly circle over 360. And now what I'm going to do is I'm going to plug everything in. I'm going to call AL X because we're looking for that. And I feel that trying to move around AL might be a little confusing. The radius is 14, so I'm plugging that into the equation. And my reference angle is 315, where squiggly circle goes. A couple of my students asked me to use a lot of colors, so there we are. We have a lot of colors. So now you're not going to see it thanks to the magic of the pause button, but this is going to take me forever to solve. So first thing I'm going to do is I'm going to reduce and try to make my problem simpler. So let's get started with that. So let's start with 2 times 14, which is 28. So where I had the radius here before, I now have the diameter. This is an important concept that's often overlooked with the circumference of a circle, because the circumference of a circle is not really 2 pi r, it's really diameter pi equals circumference. And that's kind of a slightly overlooked thing in the public school setting. Now, from there, I reduced my fraction, and I got 7 over 8. Now I am going to cross multiply and solve. Okay, and before I do so, I want to bring something up about pi. Pi is not 3.14. 3.14 is a rough approximation of pi. I might have brought this up in a previous video. It is kind of a sticking point for me because it's one of those things that we convert pi to 3.14 and in essence are making math harder than it needs to be. The ancients and forward make symbols in mathematics to make things easier to move around. I'm a true believer in the idea that as students use the math and use the math as it's intended to be used, they will eventually see what's going on and kind of see through the ether that is mathematics, and they'll get past that foggy, misty space and start to see through it. So oftentimes by converting things to 3.14 or converting things to decimals, we kind of lose that. So I'm going to leave pi, and therefore all I will be doing is just kind of moving things around. So let's do that. So 8 times x is 8x. Then 28 pi times 7 is 196 pi. Now, from there, I just have to divide that 8 away from the x. And when I do that, I get this situation with 196 over 8 pi. And I have also brought this up quite a bit. The use of a high quality calculator comes in super handy. And I have my TI 36X Pro, which will actually reduce the fractions in terms of pi. And when I did that, I have 49 pi over 2. Very nice and clean. Much easier than moving pi around as 3.14. Now, there's another issue here that I think will make keeping pi simpler. And that is that you're using the same rules as you do when you solve for x. Like, in other words, pi behaves like any variable or any square root. Those rules never change. You can't combine pi terms with non-pi terms. Pi terms or pi doesn't communicate well with other numbers, so it kind of just hangs out, much like x or a square root will. And if you're familiar with those rules, as I've mentioned in previous videos, and as I keep saying, are videos probably infinitely present in the YouTube, right? You can now manipulate these equations very easily. Okay, let's take a look at the next example. Okay, this example will require the use of sector area. So sector area is, we're going to call SA, and then we have pi r squared equals squiggly circle over 360. And now I'm going to plug everything in. Okay, so I'm going to start with x here. Then I'm going to insert the radius. Now let's get the other side of the proportion going, which means my reference angle is 90 degrees. Now I'm going to start to simplify my equation so I can make it easy to cross multiply. 9 squared is 81, and 90 over 360 reduces to 1 over 4. Now I'm going to start cross multiplication, and 81 pi times 1 is 81 pi. Then 4 times x is 4x. And now I'm going to divide out that 4. And I have 81 pi over 4. Making my final answer 81 pi over 4, because that will not reduce. The nice things about this, at least at this part of the section, is the equations are almost exactly the same, except for the area of the circle, which is on the bottom of the left side of this proportion, and then the circumference of the circle, which is on the bottom of the left side of the other proportion. They handle the same way. So once you have one under control, you'll get the other. Okay, let's take a look at the last two examples. Okay, this problem here is asking for the area of the shaded region. There is quite a number of ways to look at this. Let's start with the hard way. The hard way is to figure out what the degree of each section is. And that's not necessarily that difficult, because we have 1, 2, 3, 4, 5, 6, 7, 8 sections. And when I take 360 and divide it by 8, I get 45. So that means that each of these sections is 45 degrees. And I'm not going to write 45 all throughout them, but that means when I set up my arc length, sector area formula with pi r squared, I could just multiply 45, 1, 2, 3, 4, 5, so 45 times 5, which is 225, over 360. Or what I can do, and this is part of the place where I try to push students to understand how these formulas work and why they work, is I can just use the 1, 2, 3, 4, 5 sections out of 8 and make that side of the equation. So I could just set this up as sector area at pi 5 squared equal to 5 over 8. Now, what you can do is you could take that 225 over 360 and reduce it, and you will find that when you reduce this, you will also get 5 over 8. Things like that are the beauty of mathematics that we often overlook. It does not matter sometimes how we approach a problem as long as we are using the rules, which never change. Now, I am going to solve this. So I'm going to call that x, then I have 25 pi equal to 5 over 8. I'm going to cross multiply and solve just like I did before. So now I get 125 pi equals 8x, and I'm going to divide by 8. So x is equal to 125 pi over 8. Okay, let's address one other thing. I'm leaving the answer 125 pi over 8 because I'm not doing anything with it. In other words, I'm just answering this question. So this is 125 pi over 8 centimeters, I guess. I did kind of gloss over the units. The area, this is actually centimeters squared, excuse me. But it's not like I'm actually building something. It's not like I'm actually doing something. So in this particular case, as I've mentioned with square roots and radicals, because I'm not actually doing anything, this is the most precise answer. If I had to convert this to a decimal, the rounding that I would do would be dedicated to my measuring tool. And that's how I would have to work the problem from there. So for example, if I was using a tape measure, the smallest decimal I have is a 1/16 of an inch, which is, let's see, 0.06. If I had millimeters, I have a hundredth of a millimeter, 0.01, 0.1, 0.02, all the way to 0.9, and then create a centimeter. So it all depends on what I'm working with. I don't know, because we're given no context. We're not being told what to build. We're not being given a box. So I am leaving this 125 pi over 8. It's the simplest thing to do right now. Okay, let's take a look at the next example. In this example, we are looking at the pendulum of a grandfather clock. This is real-world application of this. So let's take a look. When we talk about the motion of an object, we're talking about the length. So we're going to use arc length over 2 pi r is equal to squiggly circle over 360. And because we want to know how far the pendulum will travel on each swing, that's going to be what we look for. And the pendulum itself is the radius. And we know that it's moving 25 degrees over 360. Much like the trig word problems, the arc length sector area word problems are pretty nice for students that are unfamiliar with word problems or struggle with them, because all you need is a length, a degree, and we want to know which way we are going with this. So it's not saying area, we want to know how far we want to know how far the pendulum travels. So we're not asking about how much something covers, which would be area. Now from there, I'm going to go right through my process that I have illustrated 3 times now. And I'm going to use my calculator and reduce this to 5/72, which isn't that super helpful, but it's better than nothing. I'm going to get 60 pi here, cross multiply. That's 72x is equal to 300 pi. And this is just going to be an ugly problem. I'm going to divide by 72 on both sides. And let's see what we get. 300 over 72 reduces to 25 over 6. So this is 25 over 6 pi. And there we have it. I guess I should add the units. I'm kind of lazy about that. Because we're traveling in distance, this is just centimeters. So there we go. In part 2, I think we're going to be talking about some more word problems. And hopefully there, the fact that we're cross multiplying here will be a little bit easier to understand than if we used the equation directly. Alright guys, I hope you found this video helpful.